Have you ever really thought about that? You're walking home, the sun's going down, and poof, just like magic, all the streetlights flicker to life. We see it every single day, but how does it actually work? How does a simple light know that it's gotten dark? Well, today we're going to pull back the curtain on that little piece of everyday magic. We are going to decode the electronic blueprint for an automatic nightlight. We're going to find out how a simple circuit can actually see the dark and react to it. Because, the secret isn't magic at all. It's just engineering. It's a really clever, elegant electronic design that, honestly, once you understand it, is way more impressive than any magic trick. So let's do it. Let's decode that blueprint. We're going to treat this whole thing like a puzzle, taking it piece by piece until the entire plan makes perfect sense. And here it is, the whole shebang. This is the complete circuit diagram, the full plan for our automatic nightlight. Now, I know what you might be thinking. That looks a little intimidating, all those symbols and lines. But don't worry, just think of this as our map. We're going to walk through it together, step by step. To make sense of our map, we're just going to break it down into three main parts. First, you've got the power supply. Its job is to take the high voltage power from your wall and turn it into the low voltage stuff this circuit can actually use. Now, we're not going to get too deep into that, but it's a special type called a non-isolated power supply, which is super important for the safety warnings we'll talk about later. Instead, we're going to focus on the two most active parts, the sensing and logic, which is basically the brain, and the AC switching, which is the muscle that does all the heavy lifting. All right, let's start with the most interesting part, the brains. This is where the circuit actually sees the world around it and makes a decision. And the star of the show here is this little component called an LDR, or a light-dependent resistor. The easiest way to think about this thing, it's the circuit's electronic eye. Its whole job is just to react to light. But how does it do that? Well, it's actually beautiful in its simplicity. When bright light is shining on the LDR, its electrical resistance drops. It gets really, really low. But the moment it gets dark, bam, its resistance shoots way up. It becomes super high. And that single change, from low resistance to high resistance, that's the trigger. That is the signal for everything else that's about to happen. It's the circuit's way of screaming, hey, the sun just went down. Okay, so the LDR sent the signal. Now something needs to act on it, and that's where the transistor comes in. Just think of a transistor as a tiny, super fast electronic switch. A very small electrical signal tells it to flip on or off, and when it does, it controls a much larger flow of electricity. These guys are the real decision makers in our circuit. And this is where it all comes together in this perfect little domino effect. So darkness falls, and the LDR's resistance shoots up, right? Well, because of how it's placed in the circuit, that high resistance causes the voltage to rise right at the input of our first transistor. Once that voltage hits a certain point, click, the first transistor switches on, and that immediately triggers the second transistor to switch on, which then sends a nice, strong, hey, it's dark, signal to the next part of our circuit. Okay, so our little electronic brain has made its decision. It knows it's dark. But now we have a huge problem. We have this tiny, low-voltage brain, and it needs to control a big, powerful, high-voltage lamp. This whole next section is about how we build a safe bridge between those two very different worlds. I mean, really think about it. How does our little 10-volt circuit tell a 220-volt lamp to turn on? If you just hook them up directly, zap! The high voltage would instantly fry all those delicate little brain components. So how do you send that message across such a dangerous electrical divide? The solution is this absolutely brilliant little component, the optocoupler. Seriously, this thing is an engineering marvel. Inside this one little chip, there's a tiny LED on one side and a light-sensitive sensor on the other, and they are completely separated from each other. The signal gets sent not with wires, but with a tiny invisible beam of light. What this does is create a physical air gap between the low-voltage brain and the high-voltage muscle. No electricity can ever cross that gap. It's totally impossible. The only thing connecting the two sides is a little pulse of light. It's kind of like sending a message in a bottle across a raging river. It's perfectly safe, perfectly isolated. So the optocoupler sends its little light signal safely across the gap. What's waiting on the other side to receive it? This guy, the triac. If the transistors are the brain's smart little switches, the triac is the big, heavy-duty muscle. It's a special switch designed specifically to handle powerful AC electricity. It gets that safe little go signal from the light, and it does the actual hard work of turning on the lamp. All right, we've met all the key players, right? We have the LDRI, the transistor brain, the optocoupler bridge, and the triac muscle. So now let's put it all together and just watch the full sequence from dusk till dawn. You know, when you really boil it all down, the logic is just so clean and simple. This table says everything. In bright light, the LDR's resistance is low and every single component stays off. But in darkness, the LDR's resistance goes high and that turns everything on in that perfect cascade. It's that simple. It's either day or it's night. And let's just watch that beautiful chain reaction one more time. 1. Darkness falls. 2. The LDR's resistance skyrockets. 3. The transistors flip on. 4. The optocoupler's internal light turns on, sending that signal across the air gap. 5. The triac sees that light and flips its own heavy-duty switch. And 6. The 220-volt lamp lights up the room. It's just so elegant. Now, as cool and elegant as this all is, we have to talk about something that is critically important: safety. Remember that power supply we mentioned at the very beginning? Well, the source material is very clear about this. This circuit connects directly to high-voltage mains electricity. We're talking about the power that comes straight from the outlet in your wall. So, let me be absolutely crystal clear here. This is not a beginner's project. This design is for experienced users only. Because that power supply is non-isolated, touching any part of this circuit while it is plugged in could be incredibly dangerous. You should always use insulated tools, and you should never, ever touch any part of it when it's powered on. Seriously, safety has to be number one. So, there you have it, the magic of a streetlight. It's really just a clever series of electronic cause and effect. And now that you get the basic blueprint, a sensor triggering a logic circuit that safely switches on a much bigger device, it really gets you thinking, doesn't it? What else could you automate with a circuit like this? What would you want to turn on when the lights go out?